Ooh, painful. Get it out of the way. All right. So what I want to do to begin with is kind of talk about the way we write it down, okay? So for the first one, we're looking for a particular thing. In actual fact, when you originally learn about the sine function, you may even use x's and y's like in any equation, right? So you've probably learned in the past that when you have a function, you have something like y equals 5x plus 2, right, for the equation of a line. And if it's a quadratic, you might have y equals 2x squared plus 3y plus 1, right, if it's a quadratic. Have you learned about quadratic and linear relationships? All right, so the sine is a function as well. We could say y equals sine x, all right? And there would be a number that would be associated with that, and that's essentially what we're doing here. When we're asking you to take the sine of a number, we get a certain value for that sine. So you could say then here that the value or the number we want, y, oh, this is really running slow, equals sine of some angle theta, and we would say then that y equals sine, in this case, of 30 degrees, okay? All right? Now, in this case, we have the y. In this case, we know what that y is, and we want to find out what the angle is, all right? So the way this is written is, in this case, we would have y equals sine theta, right? And we're given the y, so this is 0.245 equals sine theta, all right? So when this appears in an equation, you'll have a number, it's going to be a decimal number, and it's going to be equal to something in the equation which is sine theta. And what we want to get is theta. That's what we want to find. We want to find the angle. So how do we then turn this equation kind of upside down in order to get the theta? And that's what we need to do in order to solve this. And this is the way it looks. You simply take the inverse sign of both sides. And what that does is it gets rid of this sign. Essentially, we simply take the sign, bring it to the other side, make it an inverse sign, and that leaves us with theta. So sine inverse of 0.245 is equal to theta, okay? It's kind of like dividing the thing off and moving it to the other side, like you divide an x off, and it makes it go on the bottom. But we write it a little differently. So this is what I need you to be able to kind of recognize, that if I get an answer is equal to some sine theta, and I want the theta, then I'm going to bring the sign to the other side and make it an inverse sign, and that's going to leave me with the theta, okay? All right? Because we're going to have to do that eventually in order to find an angle. And I didn't do that last day. I didn't write it down in an official sense. So please write this down for I think this was the last stuff that we did. Please write this series of 3 equations down so that we can see how to rearrange it when we get to some more complicated ones. Now, I didn't have to use a y there. I could have used something else, but that kind of keeps it in line with your mathematics because that's essentially what it is. And when you learn trigonometry, you'll learn in more detail why this works the way it does and all that other good stuff. But I just need you to be able to find the inverse sign to get the right answer, and so I'm introducing it to you like this. So if we end up with, in an equation, which we're going to in a moment when we do Snell's law, with a number equals the sine of some angle that we're looking for, this could be theta 1, or this could be theta I, or this could be theta R, then you need to bring that sign to the other side. It becomes inverse sign. That leaves the theta by itself, so the inverse sign of the number gets me theta. So then in the end, if someone could calculate that for me, I know we did that. You could probably just read it off of your page. Well, what did we have yesterday? 14.18. So 14.2 degrees. Yep. 14.2 degrees. Okay? All right? So that's the way it's going to look. When we're going the other way, if I've got a number in there, like a degrees, then all you're doing is sine theta, and you're turning it into the other value. You're turning it into that number value. Okay, let's now do some Snell's law problems, and this computer is just going to crawl. All right. I believe we've already written down Snell's law, but if you'd like, you can rewrite the equation, and then you can write the example, and we'll just go through a bunch of examples at this point. And I did use a fairly small font there. I can read it off. We're struggling at the back there. Find the angle of refraction for light traveling from air into diamond if the angle of incidence in air is 20 degrees. Yep.
Does it matter how, like, the temperature?
Does the temperature of the air affect the index of refraction? I don't think so. I don't know. It would be very small. We're not going to worry about a temperature effect. When it comes to the speed of sound, temperature is a large effect. But light is traveling so fast, it's interacting with those particles on such a short period of time, I don't think it has much of an effect. But I could be wrong. That's just an educated guess. Now, when doing these refraction problems, I suggest you draw a sketch of what's taking place. Doesn't have to be a perfect, doesn't have to be a perfect, line with rulers and angles. All you need is the boundary. Put in a normal. All right. Put in a ray. And have it always coming from the left so that it's consistent with what we did in our first picture. And have it coming in. Now, you could call the angle an angle of incidence, but notice I just use 1s and 2s. And that actually makes it simpler. This angle coming in, it says that the angle of incidence is 20 degrees. So I'm going to just write 20 degrees in there. Now, it's starting out in air, and it's ending up in diamond. We need the ends in order to answer this. If it's a test, I'm telling you the end of the diamond. You might remember from yesterday, but write it down on the picture. N1 equals and N2 equals. So we're going to let N1 be where the light ray starts out, and we're going to let N2 be where the light ray ends up in the end. Okay? So it's going from air. What's the N for air? 1. 1.00. And it's ending up in diamond. What's the N for diamond? Does anybody remember? Yeah. 2.42. You are not required to memorize that. But, we deal with the same numbers many times. Yep. You don't, but it's a significant digit situation. To 3 significant digits, the index of refraction of air is 1.00. If we were to go to more decimals, it would end up that it isn't 0 anymore. It would be slightly off of the speed of light in a vacuum. So what we're stating there is that to 3 significant digits, we know that the index of refraction of air is 1.00. So it is kind of important for when we round our answers at the end. If you didn't write them down on a test, I wouldn't penalize you, but in the end, it would be nice if we rounded it to 3 digits at the end. Okay? All right. And we want to find what the angle is in here. Does anybody remember which way it's going to bend compared to the normal, just based on the qualitative picture? 50-50. Don't buy a lottery ticket today. Yep. Bends towards the normal. Because what's the speed doing? It's going from what to what? Yep. Fast to slow, it bends towards the normal. All right? You know, if you don't have the sketch right, it's not a big deal as long as you do the math right. Is what we're really worried about when doing the calculations. Because I'm using 1s and 2s instead of angle I's and angle R's, because this is the angle in the air, this is theta 1. And if you had room, you could write it in that little wedge there. I just didn't have enough room. And I want to find the angle in here, theta 2. So when it asks for the angle of refraction, I'm looking for theta 2. Okay? That's what I'm solving for. N1 sine theta 1 equals N2 sine theta 2. I'm going to put my numbers in. 1.00 times the sine of, what's theta 1? Yeah, Shane? 20 degrees equals N2, 2.42 times the sine of theta 2, and I'm running into my picture, which is unfortunate, but I think I can fix that. Just like solving for x or for y or any other thing in mathematics, we want to isolate this theta 2. Right now, it's kind of stuck together with the sine, so I'm going to divide off this 2.42. Okay? Yep? I do not need to see every step, but if you, let's say you go from filling it in right to the answer and you screw it up, sometimes I give step, 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 and if you screw it up at the bottom, I can't give you a part mark for middle step. You know what I mean? It's whatever you're comfortable with. It's whether you're a gambling person. You're willing to gamble with making a mistake on that final step? That's up to you.
I did like,
Yeah,
I did like 4 plus.
whatever. Whatever makes you comfortable. How's it going? Okay, so 1.00 sine 20 divided by 2.42 equals the sine of theta 2. Calculate that and turn it into a decimal. Would you like a pencil and an eraser? It might make your life a little easier. Do we have a decimal for that? Now here's the way it works. 1 times sine 20. You don't have to press equals. Divided by 2.42. If you've got a reverse calculator, then you're going 20 sine times 1. Seems to be a little redundant. You don't need to do that. Then divided by 2.42 equals, what do we have with 3 digits? Yep. 0.14, sorry, 1. Supporters on that? We like 0.141? So now I got to get the theta by itself, and that's where we bring that sine to the other side, and it makes it an inverse sine. So that means inverse sine of 141 is equal to theta 2, which is what we want to find. Theta 2 is equal to. Don't clear your calculator when you're done getting the first. If you've got 0.141 and a whole bunch of decimals in there, then you can, if it depends on your calculator, if you got a calculator that's a forward one, you'd press second function sine, and then there's always an answer button. Does everybody know where their answer button is? It's on these types of sharps, it's the green alpha and then answer down at the bottom here. Because then you can go second function sine, answer equals Don't need to put all those numbers in. If you've got the reverse calculator, all you got to do is push second function sign, and it'll inverse that number that's up there, and it'll do it all in one shot. If you need a calculator, you need to come and grab one so you can follow what's happening in the world. What do we have for an angle? Who's got an angle? Yep. 8.1 degrees. Do we like 8.1? Yes? 8.105. 8.1 degrees. If you cleared your calculator and put in 0.141 versus if you didn't clear your calculator, you will have differences in these end decimals. But that's okay. I don't care. Yes? It would have been nice to have one more because everything seems to have three. Actually, this is only 2 digits because it's only 20 degrees. It's not 20.0 degrees. So that's pretty good. If you were to put an extra digit, that'd be fine. No worries about it. Just slowly getting you introduced to significant digits. Did we all get 8.1 something, something, something? Excellent. Good. All right. Now, we were looking for the angle of refraction, which is the angle in the material in which it's going into, but we call it theta 2 just to keep the equation a little simpler. And theta 2 is what we're looking for, and therefore that is the angle of refraction. Okay? Let's do another one. Again, you'll notice that I am not giving you the indices of refraction. Indices is just plural for index. Again, you need to know what air is. The rest of them I will give you on tests, quizzes, practice problems, etc., etc. Again, I know the font's a little small. I didn't realize that when I was making it up. Find the angle of refraction for light traveling from water to air if the angle of incidence in water is 15 degrees. Again, this is the type of thing, if you feel a little confident, get a pencil out, go ahead. Question? Yeah, you use Snell's law when doing this stuff. Now, one thing that you might want to do differently than the last one. I indicated to you when you draw your sketch to draw it like that first picture that we did. But that would mean the water would be up here and the air would be down there, and that's just not the way the world normally functions. There's very rarely water above the air. So I would, just to make it look kind of normal, put my incident ray down there, and I'd simply just say N1 is down there. So we're kind of flipping it so that it looks a little normal with water being below the air. You could do it the other way around, and you'd still get it mathematically correct. It'd be like you're standing on your head, I guess. So whichever way you want to draw it, that's up to you. Somebody tell me some numbers to put in various positions. What am I putting where?
Is water 1.33?
Was it 1.33 the other day from water? Anybody remember? I think it was too, 1.33. So where am I putting the 1.33? At the bottom at N1, 1.33, because that's where I'm starting with my light. N2 is air. What else am I putting in here? Kayla, what do you got? And which way? And you don't. And we're just this. We gotta have it bended towards or away from the normal, right? And I'm not marking you on whether you do this right in this spot, right? Let's say so you could get it wrong. I wouldn't be too concerned as long as you did the math right. But which way is this one going to bend? So you're that's exciting. That's good stuff. Right. Well, let's go. What's small to big? Those are the words. Slow to fast. So it's going to go the other way. This way. Yeah. Correct. It's going to go that way. Now that's not needed to answer the question. Where does my given angle go? Where does the angle that I've given you go? It's an angle of incidence. What do you think? Kendall, what do you think? Bottom or top? The bottom, because that's where it started. It goes in the bottom. So my 15 degrees is right here. And what symbol do I give with the theta? 1 or 2? So theta 1. And that makes this theta 2. The rearranging will be the same, just like the last example we did. Fill in, rearrange, take an inverse sine, solve. That's the worst 3 ever. Sine 15. Again, some of you are realizing, oh, that N2 is going to go down underneath, right? So we could take a little shortcut here and put that one down there, right? That then gets me sine theta 2. What decimal number do you get for that? I guess minimal number of steps for this stuff. I need to see the numbers in there at some point in time, and then I want that number before you do the inverse sine. Megan, what you got? 348? 0.348. Supporters on that? 344? 344. Did you put, I don't know, 1.33, sine 15. So we're saying 344. My erasure doesn't work. Can you find why you've got a 348? Do you have it in degrees? Do you have your calculator in degrees, DEG, or D at the top? You must have pushed something wrong. Now take the inverse sine. Don't clear your calculator. Inverse sine it. However you're going to figure that out. Sine -1 of 0.344 is equal to theta 2. Theta 2 is equal to. Yeah, Shane? Did you say 20.13? These are, again, 2 digits on this. 20.1 is probably good enough right there. Well, again, when you get to grade 11, I'll tell you more about significant digits. We'll get it all straightened out. And look at the angle of refraction is larger than the angle of incidence. It bent away from the normal, just as we predicted. Good to go? All right. I thought maybe you were just studying that for something that did not make sense. 20.1. And I will come around as you're doing a little bit of work in a minute and help you out with your calculator if you're still struggling with your calculator, all right? I got 2 more examples. Again, for those of you at the back, if light is traveling from water to acrylic and the angle of refraction in the acrylic is 24 degrees, determine the angle of incidence. acrylic is nothing like water, right? So it's not like you got to have it a certain way. I would likely have, oh, we're going from water to acrylic. So it really doesn't matter, right? Because you could have your acrylic piece, like this thing here, in water, right? And then you could have the light beam coming from some kind of, waterproof device and having it go in there. So what you put at the top and the bottom doesn't seem to really matter in this case, because you'd probably be looking at it from the top, right? So then you'd have water and acrylic being either top or bottom. It makes no difference. Yep. What's the index of refraction for acrylic? Anybody remember? That was our experiment. Yep. Yeah, 1.50. 1.50. So I would, because it doesn't really matter and we're dealing with water and acrylic, I would again just have it coming in like that, like the classic picture that we started with. Traveling from water to acrylic. So N1 is the water and N2 is the acrylic. I think we're starting to get the hang of that, right? Some of you are already calculating. Excellent job. So what am I saying? Water is 1.33 and the acrylic is 1.50. And the angle, well, which way is it going to bend for our sketch? Towards or away from the normal? Towards the normal. Fast to slow, towards the normal. And the angle of refraction is 24 degrees. So this theta is 24 degrees down in here. And which theta is it down in here? Theta 2, because it's in N2. The theta 2 is in N2. So the number of the theta goes with what medium it's in. In this case, it's in the acrylic 2. And in this case, we're looking for theta 1, the initial one. And 1.33 sine, we're looking for theta 1, and 2, 1.50 sine 24 degrees? 24 degrees. Going to divide that off over there. Sine theta 1 is 1.50 sine 24 over 1.33. Sine theta 1 equals theta 1 equals. I'm hoping you're rearranging this before I'm getting it on the board. What do we have for the sine theta 1, the decimal value? So we're all on the same page. Nobody wants to share? Shane, what do you got? 4, 5, and I missed the last one. 8? We like 4, 5, 8? I'm not seeing a whole lot of supporters here. Not done yet. 4, 5, 9, 4, 5, 8? So it's 4, 5, 8, what? 8, 7, so it should be 4, 5, 9. I probably wouldn't even pick that up if I was marking it. You know what I mean? It's one of those things. So then inverse sine it, and what do we get? What do you got? Justin, what do you got? 27.3 degrees? 27.3 degrees? 27.3 degrees is the angle of incidence. And we predicted it would be bigger, right, from our picture. And it is bigger. Okay? So we could find theta 1 if we need to. I've got one more example before I'm going to let you work for a bit. And this last example has us actually calculate one of the index of refraction. So we could solve for n if we wanted to. Yep.
Can I enter that into the office, please?
Yep.
Thank you.
Thank you. I knew Mr. Petrus wouldn't have sent his either. As light travels with an angle of incidence of 25 degrees from air into an unknown transparent liquid, it results in an angle of refraction of 16.4 degrees. Determine the index of refraction in the liquid and the identity of the liquid. So just like yesterday when we used that little equation, N equals C over V to calculate an N, we can also use how much the light bends to calculate the N, which means this is really a way of measuring the speed of light. We can actually take a beam of light, put it into a transparent material, see how it bends, calculate the N, and eventually we could get the speed of light traveling in that material. Yep. That's what the C was that we worked with yesterday, right? 3.8 times 78 meters per second. Really fast. Yeah. Okay, so again, make your sketch. Again, we're going from an air into a substance, so I would put the air up here just because that's the most convenient. That's a question mark. That's what we're looking for this time. We have an angle of incidence of 25 degrees. Theta 1, 25 degrees, and an angle of refraction, so it bends down there, of 16.4 degrees. Not surprising, we're going from really fast air to something slow. Theta 2. N1 sine theta 1, N2 sine theta 2. Now, with the N being 1 because it's in air, I could actually write it down like this. Sine theta 1 equals N2 sine theta 2. Now, you don't have to, but I just want to rearrange this and show you something here for a moment. If I want to get N2 by itself, I'm going to divide away the sine theta 2 to the other side. And I'm going to get an equation that looks like this. Sine theta 1 over sine theta 2 is equal to N2. All right? In your experiment that I just handed back, I had you make a graph of sine theta 1 over sine theta 2. Sorry, I had you make a graph of sine angle I versus sine angle R, which is essentially sine theta 1, the angle of incidence, over sine theta 2. And when you graph that, and you take the slope, which is rise over run, well, you'll notice the rise is actually sine theta 1. And the run, which is this distance here, is actually sine theta 2. So when I have you calculate sine theta 1 over sine theta 2, or when I have you calculate rise over run, what you actually are finding is N2. That slope of that graph that I made you find is actually a scientific way of finding the index of refraction for a substance. Because this is really the slope of a graph that's sine theta 1 over sine theta 2. Yep. It's because it's equal to 1. And if I do 1 times sine theta 1, 1 times anything is the same as what it was. You don't have to take it away for this problem. The only reason I did this was because I wanted to compare it to what you did in the experiment. But in the end, you're right. There's a 1 on the front of this. 1.00 times sine, I'm going to fill this in for a moment, of 25 over the sine of 16.4 equals N2. And Megan has a question. No. If you want to put in the N1, please do so. All right? I was just, and notice I just put them in, right? And I even put it in here. I just wanted to point out to you that when you did this slope, you were doing that calculation. No, you could put the numbers in and then rearrange the numbers. I rearranged the equation so you could see how it's related to our slope. So you could have put all the numbers in and then rearranged to find what the number was. Not a problem. Okay? And what do we get for N2? 1.50? 1.50. What could this substance be? Yeah, it could be acrylic. Therefore, oh man, acryl. Oh, I killed it, didn't I? How do I spell acrylic? Is it right? Acrylic. Oh, I dropped the L. All right, I hate that word. It's got too many unconventional letters in it, back to back. An A-C-R-Y? Never see that. Question. Oh, then it can't be acrylic, can it? Was there another one? Yeah. It's 1.47? 1.4968? We're going to be doing an experiment tomorrow, and I needed some liquids, and something called glycerol is 1.473. Olive oil is 1.48. You got exactly 1.5? Not a big deal. Don't worry about it. It's liquid acrylic, which is not a liquid. Okay, let me just show you one thing. So I've already pointed out to you the... Oh, come on, you silly, slow computer. It's not going to let me show you the website. It's just quitting. The Snell's law sheet? Yeah. So work on that for about 15, okay? I already introduced you to it to find the practice with the sign and the inverse sign. Now it's questions like this, and you can do the rest of it. And the solutions I did complete. I took a picture of it and put it in the solutions folder for the optics unit in the course content, all right? So go ahead. I'm going to stop this recording for a moment. Yes, by all means, you can turn on that light.